All right, so now that we have an idea of zero order, first order, second order reactions, right? We kind of understand that certain things, maybe they if we double the amount or the concentration of it, it doubles the speed of the reaction. Maybe it quadruples it. Maybe it has no effect, right? These are kind of macromolecular properties that we see when we run a reaction, right? It's something that we can actually measure and we can see. But really, right, we want to be able to rationalize each of these occurrences based on some fundamental way that the particles are reacting, okay? So for us to kind of start to understand or start to think about how these reactions could be occurring, we have to be thinking about elementary reactions, okay? So if we just kind of think about three balls trying to hit each other, right? For us to get two balls to hit at the same time, that's going to be pretty easy. But for us to get all three balls to hit at that exact same time is pretty difficult, okay? And so based on this understanding, we say that it's going to be really difficult for three particles to hit at the same time, okay? So we basically say that, you know what, these overall reactions that we see, they have to be happening stepwise, okay? We have to have kind of one step and then the next step and then the next step, okay? So what we then hypothesize, right, is that our particles, right, our molecules are going to have different shapes, and for them to have a productive reaction, we have to have a certain type of collision to occur, okay? So if we were to have CO plus NO2 going to CO2 and NO, this would be one reaction, okay? And it's all a gas phase reaction. All of these are gases, and they're going to have to hit each other to form or to get our reaction to occur. So what we hypothesize is that if we have oxygen attached to carbon, and it comes in and it hits our nitrogen dioxide on the nitrogen side, this is not going to give us a reaction, okay? Because our carbon is going to hit nitrogen. We don't want to form a bond between carbon and nitrogen, right? We wanted to form CO2. So for us to form CO2, we have to have our oxygen and carbon, our CO. It's going to hit not the nitrogen side, but it's going to hit one of the oxygen sides. And if it hits that oxygen side appropriately and with enough force, it's going to be able to form CO2 and NO. Okay? So in this case, what we've said is that our collision has to be oriented appropriately, okay? So this is our collision model where the molecules have to be oriented appropriately and they have to have enough energy, okay? So if we remember about our gases, right, they're not, all of our molecules aren't at the exact same temperature, okay? They don't have the exact same kinetic energy. Instead, we've got something that kind of looks like this, right? Where some molecules up here have more energy than here, than lower down, but our average kinetic energy, right, is our temperature, okay? And so if we have molecules hitting appropriately and they have enough energy, they can create our reaction, or they can have our reaction occur, okay? So maybe it's only the molecules that have this much kinetic energy or higher, okay? Only these molecules up here are going to be able to react at all, and only the ones that hit appropriately will be able to have our reaction occur. Okay? So for us to kind of have more reactions occur or have our reaction proceed faster, what we could do is we could heat it up, right? We can heat up each of our molecules, so our average kinetic energy will increase, and we'll have more molecules that are above that kinetic energy limit, okay? So our way to kind of illustrate this is with the reaction energy profile, okay? So what we can do is we can have, again, a graph, and this is going to be the relative energies, okay? And maybe we have a reactant up here and our products down here, okay? So this is really the reaction energy profile as the reaction proceeds, okay? So here are my reactants. Whoops, need the T in there. And then here are my products. So in this reaction, right, I've got my reactants that the average energy is here at this level, but really, right, we've got something that kind of looks like this, where our average is there, and we've got some molecules that are up in this upper tail, okay? And we need to get over this hump to get our reaction to occur. So all of these molecules that have enough energy that they're up here, right, they're going to be able to go over the transition state. This is our transition state, okay? All right, so this is where we think that, right, we've got kind of this carbon interacting with the oxygen, right? It's kind of close enough, and it's kind of breaking that bond with the nitrogen, okay? So we've kind of started to form this bond between carbon and oxygen, and we've started to lose the bond between oxygen and nitrogen, okay? And this is our transition state. It's a theoretical spot where really it's going to be higher in energy, right, than either our reactants or our products. And so it's going to be higher in energy up here, but it's kind of that intermediate point between us having our reactants and us having our products. And only some of our molecules, like I said, have enough energy to hit and have our bonds kind of breaking and forming. We're going to be able to go over that transition state and get to our products. All right? So if we have our reaction energy profile, right, what we can start to talk about is our reaction mechanisms, okay? So reaction mechanisms are really how we think about kind of the steps of our reaction that could be occurring. And you guys aren't going to have to come up with a reaction mechanism. What you're going to have to be able to do is just kind of evaluate those reaction mechanisms, okay? So let me flip over a couple of pages here. So our reaction mechanism, let's go back to our same reaction that we said. We had CO and NO2 going to NO and CO2, okay? So our reaction, like we said, has to occur in steps, only one step at a time. So maybe a possibility would be that NO2 could react with another NO2 molecule and could form NO3 and NO. And then this NO3 could react with CO and form our CO2 and NO2 here. So if we add these two reactions up, we will see that, right, our NO2 here cancels with this NO2, so we only have one NO2 on the left. That matches with our overall reaction. We have a CO molecule that's on the left, that matches up. And our NO3 molecule here came from the NO3 molecule that was the product of the first reaction. Okay, so our first piece with our reaction mechanisms is they have to add up to our overall reaction. Okay, So in this case, we do add up to our overall reaction. That's good. But with our elementary steps, we can actually understand the rate law, or we can write the rate law for our elementary steps, okay? So what I'm going to do is I'm going to pause and I'm going to go to the next video.